Hi, my name is Maximilian Ulmer and I'm a research scientist at the German Aerospace Center. I'm excited to introduce you to our latest work, Conditional Latent Diffusion Models for Zero-Shot Instance Segmentation. In this work, we propose to formulate zero-shot instance segmentation in a latent diffusion framework to learn object matching and mask generation end-to-end. This work was created with my colleagues Wout Berdijk, Rudolf Triebel, and Maximilian Dorner. Accurate and robust instance segmentation of objects is a key computer vision task, plays an important role for many applications such as robotics. The classical approach trains a model on a priori known object classes on an existing dataset. This approach is highly accurate but lacks flexibility. If the set of objects changes or a new object is added, the model usually has to be retrained. On the opposite side of the spectrum are open set models, such as the Segment Anything model or Grounding Dino. These models have been pre-trained on vast amounts of data and don't need to be retrained for specific objects. However, they lack the ability to assign specific labels to their prediction. Although one can prompt them for labels like mustard, usually the object classes entailed in an image are unknown beforehand, and one can only prompt them with generic labels such as object. This will result in a set of generic segmentation proposals that lack the direct association with a queried object label. To this end, zero-shot instance segmentation bridges this gap by predicting instance-specific segmentations without model-specific training. Most modern approaches employ two stages. A zero-shot promptable object segmentation model, such as SAM, is used to extract segmentation proposals from an input image. These proposals are matched against rendered templates by a usually classical similarity score, such as the cosine similarity. In this work, we present OC-DiT, a novel zero-shot instance segmentation model that utilizes latent diffusion to combine object hypothesis proposals, feature matching, and mask generation end-to-end. We pose instance segmentation as a conditional generative process. This means that we guide sampling of our desired distribution by conditioning the diffusion process on target objects and the input image. In practice, we train a denoising function to model this conditional distribution at different noise levels. At inference, we then use this denoiser to evolve the distribution from pure noise until noise-free data is revealed. Due to the very specific statistical requirements of modern diffusion frameworks, we employ a pre-trained variation autoencoder to compress binary masks into a low-dimensional latent space. This allows us to shape the statistics of the latent space and improve computational efficiency. During training, we compress training segmentations using our variation autoencoder and corrupt them with noise. The corrupted segmentation tokens are concatenated with image features before they run through a number of OC-DiT blocks. Each block consists of a cross-attention layer followed by self-attention and an MLP. During the cross-attention stage, the segmentation query tokens cross-attend to tokens of objects that we inquire. Most importantly, we rearrange the segmentation tokens such that the tokens that are responsible for one binary mask can only attend to the object tokens of its assigned object class. This drastically reduces the computations required during the cross-attention stage. Each block also embeds the information of the current noise level. The VAE on the right is not used during training, and for the loss, we simply use the L2 loss of the reconstructed segmentation tokens. As object conditions, we use a set of templates that we tokenize using a ViT backbone. During training, we use a variety of different templates from different synthetic sources, such as rendered from an icosphere around the object, from datasets where the objects are rendered in random poses, flying with HDR lighting, and upright. During inference, the source of the templates depends on the application. For instance, for model-based tasks, we use templates stemming from an icosphere. However, due to our training, all images work, and the user could simply take a few photos of each target object and run the segmentation. At last, we evaluate our method on the highly adopted Bob challenge and the model-based 2D segmentation of unseen objects track. To this end, we trained two models. One that coarsely matches the entire image against the possible object classes functioning as a zero-shot detector, and the second model refines each object proposal individually, conditioned on only one object class. Our model shows strong performance, achieving state-of-the-art on two challenging datasets. For more experiments and evaluation, please refer to our paper. Thank you so much for looking at our video and your interest in our work. The code will be available on GitHub, and please find more details in the paper. If you are at ICCV, please come around and join us for a chat at our poster session.